For the last part of today's lecture, I would like to talk about buckling, because buckling is the most likely place where geometrical nonlinear finite element method is applied in aerospace engineering. So we are all familiar with a beam, simply supported beam under axial loading. And if we load it to a critical level, it will buckle. If we plot the force versus deflection plot, the equilibrium path will originally follow the vertical line, which means that there is no deflection and there is only shortening of the beam. Once we load to a critical level, which is a Euler buckling load, the beam could deflect either way, either up or down. And this is the theoretical limit of buckling for this simply supported beam. At the point of buckling, we have, mathematically speaking, a loss of solution uniqueness, which basically means that at this level of loading, my deflection, vertical deflection, could take any value along this line. And this tangent is 0. So this is called bifurcation, which means that now at this point, the structure will have two possible solution paths, either follow the original path or deflect along the new path. Now, putting it into context of our nonlinear analysis, I'm sure you're already familiar with this plot. Previously, the tangent, which means the tangent stiffness, becomes 0 when we have a limit point. Now, I've also mentioned that there is a 0 tangent at the point of bifurcation, which means that now, in a higher dimension situation, we could reach a state of loading such that our tangent stiffness becomes singular along a certain direction before reaching the limit point. And our solution could then take a secondary path, which is orthogonal to our original path. Physically, this means that our new displacement is orthogonal to our original displacement solution. So, for instance, along this path before buckling, we have only the shortening of the beam along the x direction. And after buckling happens, we have the vertical deflection, and the two directions, they are orthogonal. Now, take the example of the simple truss structure that we worked on during the last practical session. We know that after we apply the loading until a certain level, we will reach a limit point, and then it will snap through. Now, imagine now that we replace the truss with a beam. What could happen as we load further is that the beam may buckle even before we reach the limit point, so that our solution, once reaches the bifurcation point, takes on the secondary path, and then we'll never reach the limit point. So that is a possibility. Physically, this is a likely event, but numerically, the finite element solver will usually continue along the original path, unless we give it a slight perturbation, for instance, perturbation force or some initial geometrical or material imperfection. Mathematically, this loss of solution uniqueness or bifurcation would mean that our tangent stiffness becomes singular along a certain direction. So we have now our tangent stiffness composing of our material tangent and geometric tangent stiffness. We know that material tangent stiffness is of this expression, and geometric tangent stiffness for this case of a beam scales with respect to our axial force loading. And in this case, we are applying a compression, so P0 is approximately minus P under the assumption of small strain. This one changes with the loading, while the material tangent, we consider a small strain, a linear problem before buckling, then this material tangent stiffness is unchanged until buckling. Now we have at critical load, we consider this whole integral to be a unit or reference geometric tangent stiffness. So at critical load, our geometric tangent stiffness is minus P critical times this K reference geometric, and this whole tangent stiffness matrix would become singular. So this is the level, and this indicates that now we've reached the critical load level. By singular, it means that there exists a non-zero vector such that K multiplied with this vector becomes 0. If we plot this vector, then we would see it represent a certain mode of deformation. We call it a mode shape, and V is the eigenvector. The meaning of having this singular tangent stiffness matrix and this non-zero eigenvector is that if we were to have this equation where our tangent stiffness matrix multiplied with the displacement dA equals our residue, now I can add to this displacement correction an arbitrary scaling of this eigenvector and still get the same residue, which means that having this additional deformation mode is not contributing to any internal force. This is basically the mathematical representation of the secondary path here. So at a fixed level of loading, we can add an arbitrary scaling of the v vector to our existing solution, and still it doesn't change the residue or doesn't change the internal force vector. So now our tangent stiffness matrix becomes singular at two different events. One is that it becomes singular at the limit point, which means that the product of k with dA, which is the along the original path, equals to 0, and the product of k with v, which is the secondary path, is also 0. How do we predict buckling then? How do we predict this limit load bifurcation point? The easiest way, or the fastest way, is to perform a linear buckling analysis, also called eigenvalue buckling analysis. Taken, for instance, an arbitrary structure, the first step is to perform a linear finite element analysis by applying a unit or reference external force to this structure. So everything remains linear here. The objective is to obtain a stress and load distribution over this domain on all the elements. Then with this stress, we can then calculate a certain geometric stiffness matrix for all the elements over this domain. And then we assemble all this geometric tangent stiffness matrix, and we obtain a geometric tangent stiffness matrix for the whole mesh with respect to this reference loading. After obtained this reference geometric tangent stiffness matrix, then we can calculate the load level at which this tangent stiffness matrix becomes singular. When it becomes singular, then this lambda critical multiplied with the reference loading will be our buckling load, and V is our buckling mode shape. So basically this is because our geometric tangent stiffness scales linearly with our loading. So if I apply just a unit load, I can still obtain this part. After obtained the K reference geometric, then if I apply a higher load, I simply scale it. I would then obtain the new geometric tangent stiffness with respect to a higher level of loading. And as I increase my load, the nature of this tangent stiffness matrix would change. And eventually at the critical level of loading, this whole thing becomes singular with respect to a certain direction of deformation. And this mode of deformation is our buckling mode shape. There are certain assumptions and limitations to this linear buckling analysis. The very first assumption is that the structure must behave linearly before buckling. So here again, I emphasize that we are performing a linear FE with a unit or reference load to obtain the stress and load distribution. Second assumption is that the actual geometric stiffness scales linearly with our loading parameter. That is how we can then estimate the actual geometric tangent stiffness at a critical load by simply scaling our reference geometric tangent stiffness with respect to the new loading parameter. The limitations are that this method often overestimates the buckling load because we are performing a linear FEA. There are no linearities considered. The geometry of material are usually considered to be perfect. And we obtain the mode shape, but we do not obtain the actual amplitude of the deformation. And of course, since we don't know the amplitude of deformation, we cannot do any realistic stress analysis based on these results. So if we want to get a more accurate estimation of the buckling load and do a realistic stress or damage and failure analysis of the structure, then we need to perform a nonlinear or post-buckling analysis. The first step is to introduce the initial imperfection, such as a perturbation load or initial offset from straightness. This could also be a material imperfection, such as introducing a weakness in the material at a certain location. And in terms of geometric imperfection, one popular approach is to include a small amount of the first buckling mode that we obtained from the linear buckling analysis. Then the second step is to perform a full nonlinear finite element analysis, including geometrical nonlinearity and possibly also material nonlinearity. Then The result is that now we have a more gradual deformation, so it deviates from linearity and gradually goes into buckling. So the larger the imperfection, the smoother is the transition from linear to buckling. This is a realistic modeling of the behavior of the new structure with imperfection. We can perform a detailed stress or damage failure analysis based on these results, and it gives us a more realistic prediction of the peak load, because now we've considered imperfection, and this is extremely important for imperfection-sensitive structures, such as a shell, a cylindrical shell. In the first lecture, we've shown that for this cylindrical shell under axial compression, there is this snapback behavior. And this curve is with respect to a perfect shell. In reality, however, the shell could have imperfections such as no uniform thickness or deviation from perfect circle. It would behave something like this. There would be a very big knockdown factor for the buckling load. And there we need to perform a nonlinear buckling analysis with imperfections to more realistically estimate this buckling load. So this knockdown factor could be more than 50%. So many times for thinner shells, it could be even 80%.